Classical fields, like physics, matured over centuries through the rigorous testing of core laws. They grew by observing the universe, extracting patterns, and validating them until they became the recognized rules of the physical world. Design science, by comparison, is still a young field of investigation. Its earliest foundational treatises only emerged in the mid-20th century. This relative youth creates a bottleneck. The discipline currently lacks a standardized nomenclature and a consistent method for validating its fundamental rules. When researchers attempt to organize design knowledge, they typically group it into three main categories: heuristics, guidelines, and principles. To advance the field, we have to look across decades of literature to formally define these terms and map how they are actually extracted from engineering practice. Establishing these distinctions allows the field to move from isolated case studies to a searchable, cumulative body of engineering knowledge. In current engineering literature, researchers frequently use terms like technique, rule of thumb, and principle interchangeably. These figures illustrate the scale of the problem. In an analysis of 67 seminal sources spanning diverse fields like social psychology and artificial intelligence, there is a wide distribution of how design knowledge is categorized. This semantic overlap makes it difficult to transition from raw, localized experience to a universally applicable science. The goal is to extract precise definitional boundaries from this varied body of work. To do that, we need a framework that can map each concept across several dimensions of evidence and formalization. Mapping these definitions provides the framework researchers need to test and repeat design experiments with consistent results. This framework uses four specific dimensions to classify design knowledge: supporting evidence, specificity, formalization, and modality. The first two axes, evidence and specificity, track how knowledge moves from isolated intuition toward extensive empirical proof and broader application. The formalization and modality axes track the shift from informal instructions to highly formalized theories that describe how a system functions. The most basic tier is the heuristic. It plots toward low evidence and low formalization, while remaining highly prescriptive. Formally, a heuristic is a context-dependent directive based on intuition, tacit knowledge, or trial-and-error experience. A heuristic does not guarantee an optimal solution. Instead, it provides a quick and dirty method to reach a satisfactory outcome when resources are limited. In an engineering context, this acts as a strategy to reduce search time when the exact parameters of a problem are unknown. While heuristics are useful for rapid problem solving, their lack of supporting evidence prevents them from serving as universal laws. Moving up the spectrum, we find the guideline. This tier requires higher evidence and formalization, while remaining firmly prescriptive. Guidelines are directives based on extensive experience and empirical data, intended to increase the chance of reaching a successful solution. These are often formatted as grammatical imperatives, direct recommendations that tell a designer exactly what course of action to take. However, guidelines remain context-dependent. They must be continuously updated to reflect changes in technology or the environment. For example, a documented rule ensuring specific component alignments within a designated factory environment is a guideline, not a universal law. Guidelines possess the documentation that heuristics lack, but they remain tied to specific applications. At the highest tier of the spectrum is the design principle. This represents knowledge with maximum empirical evidence and formalization, but it shifts away from being prescriptive. The formal definition of a principle is a fundamental rule or law, derived inductively from extensive empirical evidence. Unlike guidelines, principles are generalizable. They cross the frontiers of most engineering designs rather than being tied to one specific mechanism. Directives tell you what to do. Principles describe the rules that govern the design itself. They are assertions that guide foundational decision-making. An example would be the underlying thermodynamic or mechanical laws that dictate the design of design, regardless of the product being built. As design knowledge matures, it gains empirical evidence and transitions from specific, step-by-step instructions into general, descriptive laws. When identified correctly, design principles function as the foundation for new tools and techniques capable of addressing large-scale, cross-cutting engineering problems. If a true design principle requires extensive empirical evidence, we have to ask how researchers are actually extracting them in practice. By analyzing the current methodologies used in the literature, we can see exactly where these rules come from. This chart shows that inductive research, the process of extracting patterns from existing data, massively dominates the field. Researchers are primarily acting as data miners. They analyze large sets of consumer products to find repeating patterns. They also parse thousands of patents and observe natural phenomena to deduce laws for biologically inspired design. This is an inductive process, gathering observational data first, identifying the patterns within it, and then developing a theoretical principle to explain those patterns. While this is effective at identifying what exists, extracting a pattern from a product is only the first step toward proving it is a universal law. That brings us to the next step in the scientific method, validation. This figure categorizes the ways researchers attempt to validate the principles they publish. The data shows a significant gap. A large portion of the reviewed publications fall under not specified or not applicable, meaning they do not explicitly define a validation methodology. When validation does occur, it typically relies on a design project, which often consists of only 1 to 3 isolated design problems or student case studies. Testing a concept on a small number of isolated tasks is often insufficient to classify it as a foundational law. To increase the repeatability of these findings, researchers are proposing more formalized computational validation techniques, such as asymptotic convergence analysis. This method tests a large dataset of source material until the discovery of new principles hits a horizontal asymptote. This provides a numerical way to show that a set of principles is stable. Researchers also suggest expanding into alternative validation methods, including agent-based modeling and Bayesian statistics, to stress test these theories. For design science to achieve the maturity of classical physics, it must bridge this gap, moving from isolated case studies to computational validation capable of building the complex systems of the future.